afternoon to everyone. I would like to present my study entitled Efficiency Analysis and Forecasting of Vaccine Resource Demand. Before I proceed to my presentation, I wish to express my gratitude to all who, in one way or another, have given their most valuable and immeasurable support and time to improve my study and made it relevant and understandable. Again, my heartfelt appreciation and thanks. Yours truly, Miss Rachel Torres Aligado. May I include in my words of gratitude to my advisor, Dr. Gilbert M. Tumibay. Let me begin my presentation by showing the presentation outline. First, I will discuss about the background of the study. Next will be the objective of the study, and then methods, the statistical analysis of data, recommendations during the proposal defense, result and discussion, and finally, I will discuss the conclusions and recommendations. The background of the study. To start, let's first discuss how the expanded program on immunization started. The expanded program on immunization was developed in the Philippines in 1976 to provide free vaccines that protect babies and children from standard vaccine preventable diseases, diphtheria, measles, tetanus, whooping cough, polio, hepatitis B, and tuberculosis. In the Philippines, the immunization programs are conducted in the health center and delivered by trained health workers. The expanded program on immunization has not yet adopted a computer-based model to determine its annual and monthly demand for national immunization vaccines. The number of vaccines provided is based on the target population. The formula to calculate the target population is by multiplying the total number of population by the percentage of live births. After calculating the number of people in the target population, this will be multiplied to the number of doses required in the EPI schedule. Figure 1 shows the flow of the EPI vaccines distribution in the city. The Department of Health Regional Office is the one who delivered the needed vaccines for the City Health Office of Cabanatuan on a quarterly basis. The EPI vaccines are distributed to all rural health units in the area. The RHU clinics serve as the main source of the EPI vaccines for rural communities. Vaccines have expiration dates. That vaccine must be planned standard to the minimum value of the predicted error range. One of the cornerstones of effective vaccine management requires accurate vaccine forecasting and sufficient stock ordering. The underestimation of vaccine demand may reduce vaccine coverage and stockouts, while overestimation leads to wastage of vaccine. According to Mueller 2016, demand forecasting systems avoid stockouts when there are significant changes in demand for vaccines. This study focuses on efficiency analysis and forecasting of vaccine resource demand. The study aimed to establish an efficient model for forecasting the vaccine stock for immunization needs. The result will help the government determine vaccine requirements so that the immunization program will not be interrupted due to stock shortage. In recent years, many studies were conducted to forecast vaccine demand using various models. Chu et al. Used the RIMA and backpropagation neural network to develop a computer-based forecast and a decision support system to forecast and allocate the annual vaccine demand for a specific vaccine of Taiwan, so that the government immunization authority can take this result to make a better decision for budgeting and purchasing for this annual vaccine requirement. Similarly, the artificial neural network was used by Imran 2016 to predict vaccine stock for immunization needs, and that government can use the application to determine vaccine stock requirement for each clinic in Pakistan so that there is no shortage or excess of stock. Sa his no 2020 predict vaccine stock for immunization needs using ARIMA. The availability of this statistical outcome will serve as a guide to improve measles vaccination and formulate adequate policies and programs so that the morbidity and mortality due to diphtheria, tetanus, pertussis can be declined in children. Although several studies have been carried out in forecasting vaccine, this is the first research that trained and applied the random forest algorithm and automated machine learning to forecast vaccine resource demand. Moreover, more research is needed in this field to improve vaccination coverage rates. Next, I will discuss the objective of the study. The general objective of this study focuses on efficiency analysis and forecasting of vaccine resource demand for the city of Cabanatuan, Nueva Ecija. The specific objectives are: number one, to assess the efficiency and the magnitude of inefficiencies of the expanded program on immunization at the city of Cabanatuan. Number two, to build a model using ARIMA, random forest, and AutoML for forecasting vaccine resource demand. Number three, to determine the effectiveness and compare the forecasting performance of ARIMA, random forest, and AutoML using vaccination coverage data. Number four, to provide visualization of annual and monthly demand of vaccine in the city of Cabanatuan. Number five, implication of this study to the Government Immunizations Authority of Cabanatuan City. Methods. The aim of this study is twofold. First is to determine the efficiency of the expanded program on immunization at 7 rural health units of Cabanatuan City. Table 1 shows the input and output parameters used in this analysis. After determining the efficiency of the expanded program on immunization, random forest, ARIMA, and AutoML models are used to forecast the vaccine resource demand and compare the results to identify the best model. The framework of the study is illustrated in Figure 2. The historical data of immunization was subjected to data preprocessing before analysis and forecasting. The data envelopment analysis was applied to historical data to measure the efficiency of immunization services. After efficiency analysis, the random forest, ARIMA, and AutoML models were developed. The performance of the three models is compared, and the best model will be selected to compute the annual and monthly vaccine resource demand. The forecasted, the forecasted demand for each vaccine will serve as a guide for optimizing campaign timing and vaccine procurement in the city. The following are the recommendations from Proposal Defense last September 29, 2018. First, change the working title. As I mentioned earlier, my study is entitled Efficiency Analysis and Forecasting of Vaccine Resource Demand. Number two, study the area of efficiency analysis. This study incorporates the area of efficiency analysis. The study used data envelopment analysis to measure the efficiency of immunization services in 7 health districts of Cabanatuan City, Nueva Ecija. The study used input and output indicators to measure the expanded program on immunization outcome. Number 3, revise study objectives according to new title. On the slide is the new objective of the study, which is already discussed earlier. Number 4, include the processes in the manual system. The introduction includes the discussion about the manual system. It was also discussed earlier. Number 5, check the process flow of DOH in terms of distribution of vaccine. It was also included in the introduction. Number 6, include related literature. It was already added in the introduction. Number 7, use other statistical treatment. Aside from a Riemann model presented during my proposal defense, the data envelopment analysis was utilized to determine and assess the performance efficiency of the 7 rural health units of Cabanatuan City. The study also utilized random forest regression to model time series forecasting for vaccine resource demand using the H2O package. The H2O package is an open-source machine learning library that works on distributed processing and uses a Java-based library. The automated machine learning model was also used. The AutoML model used the following algorithm: pre-specified version of the XGBoost gradient boosting machine, a set of GLM grid random forest H2O GBM deep neural net, an extremely randomized forest, a random XGBoost GBM grid, a random H2O GBM grid, and a random deep neural net grid. Next, I will discuss the results and discussion. The first part of this study focused on efficiency analysis of the expanded program on immunization. After efficiency analysis, ARIMA, random forest, and AutoML models' performance are compared in terms of selected error metrics. The best model will be selected to compute the annual and monthly vaccine resource demand. The relative efficiency of RHU was determined using the input and output-oriented DEA model. The formula to measure the efficiency of each DMU is by dividing weighted sum of output to weighted sum of input. The data envelopment analysis was performed using RDEA package in R. The robust data envelopment analysis or RDEA estimates efficiency score using the input and output variables. On the slide is the figure that shows the code used in performance efficiency analysis in R. It first installs RDEA package, then load the dataset. Next is to set input variables such as target population, number of health worker, number of health center. Then the output variable are BCG, OPB, pentavalent vaccine, and measles vaccine. The last step is to perform the data envelopment analysis. Table 4 summarizes the RHU efficiency result in the city of Cabanatuan for 2019 in terms of the expanded program on immunization. The rural health unit with 100% efficiency was 1, 3, 5, 6, and 7. And the remaining 2 rural health units were classified as low efficiency and expanded program immunization services. Table 5 shows the recommendations for improvement for inefficient DMU, such as RHU2 and 4. The benchmark DMUs are 1, 3, 5, 6, and 7. The result shows that the target population, number of health workers, number of health centers must be in proportion based on the number of vaccine demand. It may also be concluded that the vaccine forecasting is necessary to improve the immunization services efficiency. Next is forecasting. This study used monthly data on vaccine coverage in Cabanatuan City, Nueva Ecija for 72 months from January 2014 until December 2019. The time series data was divided into two parts for training and testing. The training data set was used to create the forecasting model with data from January 2014 to December 2018. Likewise, the testing dataset was used to verify the forecasting model with data from January 2019 to December 2019. The R programming using RStudio software was used to build the forecasting model. The first stage is to load the libraries and the dataset using R commands as displayed in Figure 10. The raw data are not ready for developing forecasting model because the data set may have distinguishably different values from most other values. The following processing tasks was performed to improve the efficiency. First is identification and replacement of outlier data. Outlier data may severely affect the forecasting performance. Therefore, to increase the forecasting accuracy, it is necessary to identify and treat these outliers. The TS outliers function from the forecast package was used to identify and suggest potential replacement value. The mean and spread of the data before and after identified and replace the outlier are shown in a box plot in figures 11a and 11b respectively. Next is constructing and decomposing time series format. This step involves time series construction and decomposition to decipher the series trend, cycles, and seasonality. Decomposition helps understand the series and improve forecast accuracy. Number 1. Time series construction. The TS function in our library to specify the frequency was used to construct a time series. This study used a frequency of 12 and 1 to indicate that a time series is composed of monthly and yearly series. Figure 12 displays the code snippet in our language using TS function and time series plot of vaccination coverage with a parameter frequency of 12 and start with 2014. Number 2, time series decomposition. This step involved time series decomposition to understand the underlying patterns for vaccination coverage data. The decomposition of additive time series into random, seasonal trend, and observe are shown in Figure 13. Number 3. Feature engineering for random forest model. Feature engineering involves the creation of new features that can be used as informative input for the model. The package declare and lubricate were used to create trends, lag, and a seasonal component. Figure 14 shows the code and output of features creation. So the new features creation from the series which is shown in Figure 14 are first, the trend feature, a trend and a trend squared. This uses a simple numeric index to control the upward trend and the potential nonlinear trend. Next is log features or log 12. This capture the observed correlation of the series with, with its yearly seasonal lag. Next is seasonal features. These provide a categorical variable for the month of the year to capture the series seasonality. The next discussion is fitting an ARIMA, random forest, and AutoML model. So let's start with autoregressive integrated moving average or ARIMA. The first step in ARIMA model fitting is to determine if the series is stationary. To detect the time series data stationarity, ATF test from the T-series package will do the augmented Dickey Fuller test with standard hypothesis. If the p-value of H sub 0 is greater than 0.05, time series is not stationary. While if the p-value of H sub 1 is less than 0.05, the series is stationary. Based on the result of the ADF test, the p-value obtained is 0.2572. Since the p-value is more significant than 0.05, we can conclude that the data set is not stationary, as shown in Figure 15. Moreover, to make the series stationary, differentiation using the diff function was performed. The p-value of the ADF test for the series of the first-order differences is 0.01. Therefore, the hypothesis H sub 0 is rejected. We can conclude that the series is stationary and can be used for fitting an ARIMA model as shown in Figure 16. The ACF or autocorrelation function and PACF or partial autocorrelation function methods are the tools used for determination of ARP and MAQ as shown in Figure 17. The log value of ACF is 0, while the log value of PACF is 0. So it can be inferred that the ARIMA model obtained is ARIMA 010. Then, checking the ARIMA model using AutoARIMA function from the forecast package as shown in Figure 18. The best ARIMA model is ARIMA 010-10012. Next is random forest model. This study utilized random forest regression to model time series forecasting for vaccine resource demand using the H2O package. The H2O package is an open source machine learning library that works on distributed processing and uses a Java-based library. The first step is to connect the H2O and R to install and load the H2O package. After loading the package, the function H2O init was initialized. The H2O init function initializes and connects to a running H2O instance. The output of the H2O init function was shown in Figure 19, which provides information about the cluster setup. Now that we have prepared the data, created new features, and launched the H2O cluster, we are ready to build the random forest forecasting model. Figure 20 shows the parameter used for training of the model. The model used 500 trees and 5-folder cross-validation. Moreover, stopping criteria was included to handle the model's running time. The contribution of the model input can be viewed using the H2O variant plot function. Figure 20 shows the rank contribution to the input variable's model performance, normalized to a scale between 0 and 1. The trend square and trend variable are the most important variable in the model, followed by the month and other lag variable, lag 12. The output of the model contains information about the model performance and parameters. Figure 21 shows the model summary function, which contains information about the model parameter, performance, and parameters. The model summary shows that the random forest only used 32 trees out of the 500 trees that set on entries argument. It also shows that the tree depth ranged from 7 to 11 and the number of leaves per tree ranged from 26 to 38. Next is H2O AutoML. So the H2O AutoML function provides an automated approach to training, tuning, and testing multiple machine algorithms before selecting the model that performs best based on the model's evaluation. It utilizes algorithms such as random forest, gradient boosting machine, deep learning, and others using different tuning approach. The function's running time was set to 60 minutes. The function returned a list with the leaderboard of all the tested models. Figure 22 shows the output summary of the H2O AutoML function. The function returned a list with the leaderboard of all tested models. The total models trained are 44 and the best model is gradient boosting machine. Is visualization. Figure 24 shows the forecast result of monthly demand of vaccine from January 2019 to December 2019 for ARIMA model. The result shows for vaccination coverage for oral polio vaccine, BCG vaccine, pentavalent vaccine, and measles vaccine. Next, let's visualize the random forest forecasting result on the testing partition with respect to the actual forecast. The plotly function was used to display the forecast output in the form of a plot, as shown in Figure 25. Next is the forecasting result of automated machine learning model from January 2019 to December 2019. The plotly function was used to display the forecast output in the form of a plot, as shown in Figure 25. The result of the three models captured the seasonality component of the vaccination coverage series. However, the AutoML is higher with respect to the mean absolute percentage error. Next is discussion. The ARIMA random forest and AutoML model fit the vaccination data and made one-year forecast. The results are compared using mean absolute percentage error accuracy measure. In forecasting, the smaller the values of this criteria, the better the performance. Table 5 summarizes benchmarking of the ARIMA random forest and AutoML model against the existing system. The ARIMA random forest and AutoML model for forecasting accuracy are comparatively close. The result of the ARIMA model is 10.64, meaning the model has 89.36% success rate. The random forest model is 8.61, meaning the model has 91.39% success rate. And the last model, which is AutoML, is 7.46, meaning the model has 92.54% success rate. Based on the result, it can be argued that AutoML model outperformed the two forecasting models. Likewise, the result of the three models are quite close. The three models can be used in forecasting the demand for the vaccine. These findings are essential in deciding the vaccine supply specification in the city of Cabanatuan so that there is no shortage or excess stock of vaccine. Sa HISNO 2020 utilized the ARIMA model in forecasting the demand for vaccine, which obtained 8.62 or 91.38% success rate. Both studies use ARIMA and produce quite significant results in forecasting vaccine resource demand. However, the proponent study used other forecasting models, the random forest and AutoML model. Both of these models outperformed the results in the previous study. And last are the conclusions and recommendations. This study focuses on efficiency analysis and forecasting of vaccine resource demand. The study utilized a data envelopment analysis to determine the rural health unit's efficiencies in delivering immunization services. The result of efficiency analysis reveals that the target population, number of health workers, and number of health centers must be in proportion based on the number of vaccine demand. It may also be concluded that vaccine forecasting is necessary to improve immunization services efficiency. Furthermore, this study demonstrates a comparisons of ARIMA, random forest, and AutoML model for forecasting the required vaccine stock for immunization purposes. For developing the model, 6 years of data from 2014 to 2019 comprising are used. Random forest and AutoML is a machine learning technique, while ARIMA is a statistical technique. The dataset is divided into training from 2014 to 2018 and test is 2019 to ensure efficiency and reliability. The most appropriate models are decided according to their forecast performance. The result shows that the ARIMA, random forest, and AutoML models can get a good forecast in applying actual data with seasonal patterns and can be effectively engaged for vaccine demand forecasting. This research study has several implications for the City Health Office of Cabanatuan, Nueva Ecija. First, the forecast result can serve as a basis for the city government to determine the vaccine stock requirements to avoid shortage and oversupply. Second, the proposed model can ensure the immunization coverage is well distributed in every health center. Last, the forecasting result will help improve the immunization coverage of the city. In future work, a further project can be carried out on time series with trend and seasonal by applying these approaches to a broader scale, especially the combination of machine learning and statistical approaches. And that's the end of my presentation. Thank you. Dakala salamat and God bless.